Imagine you are an engineer and you are told to get a massive 40-ton cargo truck across a shallow river. The gap is small, so it seems like an easy job. So you take a long flat slab of concrete and just place it straight across the two riverbanks. It is a simple straight line. You give the signal and the truck starts driving. But the moment the truck reaches the middle, the bridge begins to sag under the combined weight of the truck and the concrete itself. That puts the top under compression and the bottom under tension. Since concrete is weak in tension, a crack forms underneath. Within seconds, it races through the slab, the bridge breaks apart, and your truck plunges into the river. You realize that making the concrete thicker won't work. It only makes the bridge heavier, causing it to snap even faster. So you step down into the river. You build thick pillars from the riverbed, placing them every few meters to support the concrete from below. Now your long, fragile bridge becomes a series of short, heavily supported sections resting on solid legs. Congratulations, you just built the beam bridge. It looks completely boring, but it is cheap, it gets the job done, and that is why it is the most common bridge in the world. Because your first bridge was a success, you get a new job. Now you are told to build a bridge across a 200-meter deep canyon. You try to use your old trick. You place a flat concrete slab across the gap and try to build pillars all the way down to the bottom of the canyon. But building 200-meter tall pillars is incredibly expensive and almost impossible. The pillars become too heavy and unstable. They collapse from their own height and your bridge falls into the gap. You realize you cannot support this bridge from the bottom. So you change the shape of the beam. Instead of a flat straight line, you build the concrete into a giant half circle, or an arch. Now, when gravity pulls down on the road, the curved shape catches that downward force and pushes it sideways. The force travels down the curve and pushes directly into the canyon walls. But there is a new problem. That sideways push is very strong. If the canyon walls are made of soft dirt or loose soil, the push from the bridge will break the dirt walls apart and the whole structure will collapse again. To fix this, you make sure to only build this bridge between solid, hard rock cliffs. When the arch pushes into the solid rock, the rock does not move. It pushes back, holding the entire bridge tightly in place. Congratulations, you used the canyon walls to carry the load. You just built an arch bridge. A few weeks later, another project lands on your desk. This time, you need to carry a massive cargo train across a wide, flat river. Because you are at a flat river, you go back to your first idea. You try to build a standard beam bridge by placing a long concrete beam across the wide gap. But as the bridge gets longer, the concrete beam becomes so heavy that it starts struggling to support its own weight. To stop it from sagging, you'd have to make it thicker and thicker, turning the bridge into an enormous block of concrete. It would be incredibly expensive, inefficient, and still vulnerable to bending. You need a completely different approach. So you throw away the solid concrete and switch to steel bars. You build a long hollow frame shaped like giant square boxes. But when the heavy train rolls in, the square shapes fail. Squares are easily deformed. The heavy weight pushes down and your steel squares squash flat to the side, just like empty cardboard boxes. To fix this, you place diagonal steel bars inside the squares, turning them into triangles. The triangle is the strongest shape in geometry. It does not squash. It perfectly spreads the heavy train's weight across the entire skeleton frame. Congratulations! You just created the classic truss bridge. Soon after, you land an even bigger project. This time, you need to build a highway bridge across a busy strait. You successfully construct two massive piers in the water, but there's one problem. The gap between them is simply too wide. You can't build temporary supports in the middle because giant cargo ships need to pass underneath every day. You remember your last success, so you use lightweight steel triangles. Standing on top of your first pillar, you start building a long, hollow truss frame reaching straight out over the water, trying to reach the second pillar. But gravity uses leverage against you. Building only on one side makes the bridge act like a diving board. The long arm gets too heavy, tilts forward, rips off the pillar, and crashes straight into the sea. Then you come up with a different approach. Instead of building the bridge in just one direction, you extend the steel frame on both sides of the main pillar at the same time. Every new section built over the water is balanced by another section built behind the pillar, keeping the entire structure stable throughout construction. Then, you build a smaller, standard truss bridge and simply drop it into the gap, letting it rest perfectly on the tips of the two main arms. Congratulations, you just created the famous cantilever bridge. You finally rest and make yourself a cup of coffee, but before you can even take the first sip, the mug suddenly turns into another engineering project. Now you need to cross a massive ocean strait that is over 1.5 kilometers wide. You try your old trick. You try to build a massive cantilever bridge, reaching giant steel arms out over the water to cross the huge gap. But the strait is simply too wide. Even after extending the cantilever arms as far as you can, they're still nowhere near reaching each other. Building another support pier in the middle isn't an option either. The water is simply too deep. You need a completely different way to cross the gap. Then you come up with a completely different idea. Instead of adding more support piers across the strait, you build two enormous towers near each shore and stretch massive steel cables between them. From those cables, hundreds of smaller hangers suspend the roadway, allowing the bridge to span distances that no cantilever bridge could realistically cross. The bridge is finally complete, but you've just created a new problem. Because the roadway hangs from long steel cables, it's much more flexible than any bridge you've built before. On a windy day, powerful gusts begin pushing the bridge from side to side. At first, the movement is small, but with every gust, the swaying becomes more violent until the entire bridge is shaking uncontrollably. So you reinforce the roadway with a deep steel truss underneath. Instead of letting the deck bend and twist on its own, the truss locks the entire roadway into one much stiffer structure. Now, when strong winds push against the bridge, the deck stays far more stable, allowing cars to cross safely once again. Congratulations, you just built the suspension bridge, one of the greatest engineering achievements ever created. After finishing that bridge, you head to a diner for lunch. You sit down and order your food, but the waiter there gave you another project. This time you need to build a bridge across a massive river running through a crowded city. The water is shallow enough to build piers, but the river is still far too wide for a simple beam bridge. And with boats constantly passing through, you can't fill the river with supports. To make things worse, your budget is tight, and there's barely any room to build on either shore. Then you come up with a clever idea. You build a single tower in the middle and run straight steel cables from it to the roadway on both sides. As the bridge grows outward, each new section is matched on the opposite side, keeping the structure balanced. The cables pull the weight of the roadway toward the tower, where the load is carried safely into the ground. Compared to a suspension bridge, this design uses less material and doesn't need massive anchor blocks, making it a simpler and more economical choice for shorter spans. Congratulations! You kept the river clear for boats, you saved the city's land, and you used straight lines of tension to balance everything perfectly. You just created the cable-stayed bridge. And just like that, you've learned something important. There's no single perfect bridge. Every design exists for a reason, and there's always another problem to solve.